Okay. The graph of a function. So we're going to take a look at a couple more mother functions, and we're also going to talk about those things that we've hinted at already by going over a problem, and that is how do you change the mother functions to get these other graphs? In other words, when you stick things into functions, how does it affect the graph? Does it slide it up, down, left, right, flip it over, flip it up and down, flip it left and right? Who knows? So first of all, some function notation. When we start talking about points on graphs now, we're no longer going to talk about random points as being x comma y. We're going to use this new notation. It might not be new to you, you may have seen this already, but we're going to use points as x, f of x. Because everything that we do here is based on functions, and so we want to stay with that function notation. X is the x that you already know. F of x is the same thing as the y value, because you know that y is equal to the f. It's just a semantics thing so you understand what we're talking about. We talked about this already, but we'll go over it again. The vertical line test tests whether or not you have a function, because if it has more than one y value for any x, it's not a valid function. That's why we talk about a sideways parabola not being a function, but we just take the top half of the square root and we're good to go. The difference would be between y equals the square root of x versus x equals y squared. One is a function, one is not. Are you all good with the vertical line test? You know how it works? Yes? Are you also good? This is a ways away, but do you remember the horizontal line test? What does that have to deal with?
Same thing, but flipped. And it's looking for more than one point on the y instead of x.
What does the horizontal line test test? Okay, we'll get to it later. It's not important right now. Vertical line test is important because we're dealing with functions.
Just if it's a function, isn't it?
I'm sorry?
Does it test if it's a function?
No. That's what the vertical line test does. We'll get to it later, don't worry. Okay, so some examples of things that aren't functions. What causes some problems there? Well, like we said, in the first one, the sideways parabola, there's two y values for one x value. That's a big no-no. But notice that in B and C, those are still functions. Okay. Even though there's gaps in the graph or holes in the graph, those pop up every once in a while. Or asymptotes, it's still a function. It's okay. This is the big no-no, is when you have two y values for one x value. It's no longer a one-to-one function. Okay. Talked about it. Yes, there's the one we haven't, there's one of them we haven't talked about. That's 1 over x. We just did kind of, but that's okay. It's asymptotic to the y-axis, and it's asymptotic to the x-axis. Are you okay with the term asymptotic?
It sounds funny.
It sounds funny? Okay. Just because it's new? Or you just think it's a funny sounding word?
Weird.
Okay.
Same voice.
Stop. That was mean.
Are you saying anything? Are you talking to him?
I was talking to Taylor.
Okay. Be nice.
I said 5-letter word.
E-L-E. Everybody love it. Sine and cosine we talked about already. So this is a new mother function for us, and then we'll also talk about the step function in a second. So we're good on all these, right? Good. There's the step function. Don't get the step function confused with the absolute value function. Notice there's 2 bars on each side. It's also known as the greatest integer function. So it takes a number, it chops off all the decimal stuff, and just gives you the integer value. So for instance, if I have a value of 1.5 and I put it into the step function, it gets rid of the 0.5 and just gives you 1. What you can't tell from this graph is that on the actual step function, when you're drawing it, for instance, each of these dashes will be one of 2 things. It's either this or it's this. Which one is it?
The top one.
Top one?
Bottom.
Bottom?
It includes one.
It can't be both.
Bottom.
Way to think outside the box though, Max, I like that.
It's a top one.
Bottom. Definitely top.
It's the top.
Yeah, definitely top. All right, let's take this. At 2, what's the value of the step function at 2? 2. So therefore, it would be the top one. And you won't see that on the calculator, but when you're drawing that, if I ask you to graph this function, I'm going to need to see the open circles and the solid dots. What you also can't see on the graph is that there is a dash right there for the values between 0 and 1. We don't do a lot with that function as far as algebra. We will do a lot with that function as far as graphing goes. So you should be comfortable graphing that. And if you're graphing the step function, you're not going to graph all 30 of those little dashes. You're going to do a couple of them just so you have an idea of, or just so you can demonstrate that you know what you're talking about. Piecewise functions. These cause problems for people. And I've seen people handle this all kinds of different ways. Some people like to graph the functions and then erase what you don't need. That's okay. It's fine. Some people only graph the chunks that you need. That's okay too. What you don't want to do is rely on your calculator. It will not help you with piecewise functions. You're going to have to be able to do this without it. So we're going to do this one together. When you're looking at a piecewise function, there are certain points that I call the funky points. Where are the funky points in this graph? Mason?
0, 2.
0 and 2, correct. There are points where there's some transition from one graph to the other. When those transitions happen, you have to be sure that you include, like it says at the bottom here, open circles and solid dots where they're needed. Okay. So I like, when I do it, I don't graph the whole equation of each individual one and then erase. I just do the parts. If you do the other one, then you might get a little lost, but I don't care which. I don't know if I put it. No, I didn't put a grid on there. Okay, so we'll do it here. Nope. Come on, Reedy. You can do it. You have this written down, right? Good. So then f of x is equal to, what was the top function? 2x plus 3 from?
X is less than 0.
Okay.
X squared.
From?
0 is less than or equal to x, which is less than 2.
Uh-huh.
And 1 if x is greater than or equal to 2.
Okay, good. Let's do that first. What is it? It's a line with a slope of dos, gracias, and a y-intercept of 3. Now, in this particular case, the y-intercept is relevant because it's in the domain that we're talking about, so I'm going to start with that. If it's not, you definitely want to take that funky point that's associated with it and use that as your starting point for a line, because it's either going to go up or down, to the left or to the right from that point. So I have a y-intercept at 3, so I come up here. Is it a solid dot or an open circle?
Open circle.
Open circle. And am I going to the left or to the right? To the left with a slope of 2. So down 2 over 1, and I get something like that. X squared. Okay, so the two values of x squared with the funky points are 0, which would be a solid dot because it's including it, and at 2. So at 2 it would be over here and up here with an open circle. And I know it's a parabola, so it's going to have a curve, something like that. Easy peasy. Now the fun one. What's the graph of 1 look like? Horizontal line through? 0, 1. But I'm not going to extend all the way over there. I'm going to start at 2. So up here at 2, solid dot.
That would be array.
or?
It is array, correct. You have like geometry flashbacks? Awesome.
I said more.
Okay. Is that a function?
Yes.
You sure? It better be, because it's a piecewise function. What would make it not a function if you did something silly like that? Now all of a sudden it's not a function. So don't do that. Make sure you're careful with your open circles and your solid dots. When you're done with the piecewise function, it still has to pass the vertical line test. So if you've got lines flying all over the place, you probably didn't erase correctly. Like if you start this back here instead of where it belongs here, you're going to invalidate the idea of it being a function. Okay, and you can do all that, right? All right. Again, don't rely on the calculator for that, because the calculator doesn't do a good job of eliminating the stuff that you needed to eliminate. Now, realistically speaking, if part of the piecewise function you have no idea what the graph looks like, you could use the calculator to get a general idea, but you should know what a cubic looks, or what a quadratic looks like, a linear term looks like, and a horizontal line looks like, hopefully. All right, so this is where we get into the refresher on how the mother functions are affected to get the other graph. When transforming the graphs, I ask myself a simple question. Is the number that you're working with attached to the variable, or is it outside the variable? Meaning, how is it, where is it located? Is it right next to the variable, like this? That 3 is right next to the variable. Or is it outside, like this? Notice it's not attached. If it's not attached, if the number is not attached, it's going to move it up and down. If it is attached, it moves it left or right. Same thing is true with the negative sign. Is the negative sign attached to the variable or not attached to the variable? If it's attached to the variable, you flip it over the y-axis. If it's not attached to the variable, you flip it over the x-axis. So identify the mother function first, then perform the transformation. The transformations happen in the same order as PEMDAS. So you multiply first, you add or subtract second. So the translations here happen, these will happen first because they're inside parentheses. This will happen last because it's outside. We will not do nearly as much work with this as you did last year. You did a ton of this last year, didn't you?
Yeah.
Yeah. Our use of this is more in the process of evaluating functions than it is trying to get a graph like that. Okay. So we talked about that already, and those are the shifts that I talked about. Okay. Not attached to the variable, moves it up and down. Attached to the variable, moves it left and right. Not attached to the variable, reflects it about the x-axis, and then there's all of those things combined. And notice the order that happens there. You would move it 3 units first, then reflect it, because you do parentheses first, then multiplication, division, then addition. I think that wraps it up for us. Yeah. This chart is in your book, so I think, just let me make sure we're done. Yeah, so we're done with day 6. Quick joke for you before I go back. Okay.
Wow.
Back to the
That one?
That does make
No,
sense.
the other one. One more.
That,
Yeah, that one.
So true.
We have day 6 tonight.
day 6 tonight. Which, okay, hold on, let me finish recording, stop recording this.